Above, we constructed the Fermion annihilation and creation operators. We used those to construct a wavefunction operator that had some potentially useful properties. Here we're going to start to use these to rewrite other operators, especially Hamiltonians. This new way of writing operators will automatically take care of the multiple particle aspects, including all of the anti-symmetrization with respect to exchange. This will lead to a simple way of representing fermion operators, valid for both single and multiple particle systems. Indeed, that is one of the beauties of this approach. We can now write down a form of an operator, such as a Hamiltonian, that we can use independent of how many particles we're considering. Previously, we would have had to rewrite the operator if we added in more particles, adding new coordinates and new derivative operators and so on. Now we can avoid that. This economy of notation is one reason why this annihilation and creation operator approach, sometimes also called second quantization, is so widely used as a notation. Because it's a very economical notation, we often use it even if we're not doing anything particularly complicated in our quantum mechanics. So you're likely to see it as a convenient way of writing quantum mechanics, even for quite simple systems. Now we're going to consider progressively more sophisticated cases of fermion operators, showing how these can be written using our creation and annihilation operators. Suppose we consider a Hamiltonian for a single fermion. Now, previously, we had a simple Hamiltonian, such as essentially the simplest Schrödinger equation for a single particle. The Hamiltonian there was just in this form. For a given state psi of spatial wave function, therefore, psi of r, the expected value for energy was just this kind of expression. The expected value for energy here in this notation was this form in Dirac notation, which in integral form looks like this. So this is the expectation value of the energy. We have the wave function over here, the Hamiltonian operator, and the complex conjugate of the wave function over here in the integral notation. To give the Hamiltonian fermion particle character, we're going to substitute for the wave function in this kind of expression with the wave function operator, generating our desired new fermion operator instead of the expectation value. So that's our trick here, using the wave function operator. Hence, we're going to obtain a single particle Hamiltonian operator that is simply, we propose, in this form. So it looks just like this expression for the energy expectation value, but instead we have the wave function operator and its Hermitian adjoint here, and we're postulating that this will give us a good way to write down the Hamiltonian. So it's just a postulation, but we're going to show that it works. Presume that the single particle basis states we're working with these spatial wave functions, phi m of r here, are actually the eigenstates of the single particle Hamiltonian. So these are the wave functions of the energy eigenstates. That's what we're going to start out with anyway. And these have corresponding eigenenergies, Em. Now we're going to use our wave function operator, and we will obtain this kind of expression. So all we've done is we've substituted in, using this wave function operator form. Remember, we had the wave function operator over here. Well, now we have that. We've got the sum over k of bk phi k of r. So that was our wave function operator on the right. And on the left, we had the Hermitian adjoint of our wave function operator. And here, that will be this sum with bj dagger, the creation operator for state j, and phi star j of r. So that's the Hermitian adjoint of the wave function operator. And of course, we have the sum over two indices here. So let's work through this expression. We can simplify it. Well, this operator, operating on one of the energy eigenstate wave functions, just gives us the energy of that state times the wave function. So that's the effect of this operator operating on that state gives us Ek times phi k of r. So all we're left with in the integral now is phi star j of r, phi k of r. Well, these are orthonormal functions in general. So only if j is equal to k does this integral leave us with any value, and if so, it leaves us with the value 1. In other words, it's just the Kronecker delta, delta jk, the usual orthonormality relation. So we're left with this expression here, and we can simplify that a little more because all we're saying is that j and k have to be the same index, so we lose one of our summation indices, and we're left only with the sum over j. So now we're proposing that the Hamiltonian operator can be written in this form, which is very elegant. And we can go one step further if we want to, and note that of course this is just the number operator for state j. Either one of these two forms will work. Actually, this one is perhaps slightly more common. Now we can use this rather elegant form here. Consider a state phi, which is a linear superposition of the basis states. In the R representation then, phi would simply look like this. This is our linear superposition of basis states. Or equivalently, in the number state notation, we would have this kind of expression. The same expansion coefficients, and now we're writing Bm dagger operating on the empty state, which gives us a particle in state m. As we said, this is a convenient way of writing the basis state in which only single particle state m is occupied. The Hermitian conjugate of this state here is simply the following bra vector. So we simply take the Hermitian conjugate of each of these products in here, which as we know is the flipped around product of the Hermitian adjoints or conjugates. So now we can formally evaluate the expectation value with our new form of the Hamiltonian, which we hope is going to work here. So we've got our new form of the state and we've got our new form of the Hamiltonian. So let's work it out. We're putting in our new form of the Hamiltonian. We've got our new ways of writing these states here. Well, if we put all this together, this is the state on the right, this is the state on the left, and in the middle we have our Hamiltonian operator, which you might remember is the sum over j of ej, bj dagger bj. So we put everything together and we get this expression here, and perhaps for the moment this looks rather frightening. But we can simplify this. So we're going to take this part here and just simplify it. And how we simplify it is by using the anti-commutation relations. So a simple algebraic approach to simplify an expression like this one is to use the anti-commutation relations to push annihilation operators to the right. In fact, that's basically what you're always going to do when you see a complicated product of annihilation and creation operators. You're going to use the anti-commutation relations everywhere you can to push annihilation operators to the right. That's the trick. And that will lead to disappearance of terms because an annihilation operator acting on an empty state gives a zero result. So if we manage to push annihilation operators to the right, they'll be operating in an empty state, and all terms with annihilation operators on the right operating on the empty state will vanish. So we'll keep making substitutions of this form. We see a pair like this with the annihilation operator on the left, the creation operator on the right. Then we use the anti-commutation relation to substitute this expression. And you see now we've got a Kronecker delta and we've got an annihilation operator on the right. This is the same as we did before, and we're just going to keep on doing this. So as I said, this is just the anti-commutation relation for these two operators. Hence, let's do this. So first of all, here's a pair, annihilation, creation. So we use the anti-commutation relation to flip them around here with the Kronecker delta. So bj bn dagger is equal to delta nj minus bn dagger bj. And similarly for this pair, bm bj dagger turns into delta mj minus bj dagger bm. We've used the anti-commutation relation with each of these pairs to push the annihilation operators to the right. Well, we can deal with this one first of all. We've got bj on the right operating on the empty state. So this term vanishes, and we're just left with the delta nj times the empty state. And then we can do the same trick again. This is just a number, of course, the delta nj. So now we have bm operating on the empty state. So this term must disappear. So all we're left with is these two Kronecker deltas times the empty state. So we've simplified down this expression to just this one here. So we can substitute back into this expression we had with all of this stuff. We're going to substitute this instead. And that just leaves us with these two Kronecker deltas, the empty state as a bra vector times the empty state as a ket vector. Well, that's just going to turn into 1. And when we operate with our two Kronecker deltas in here on simplifying the sums, well, we're going to lose both the sum over m and the sum over n and just be left with the sum over j, in which case we have cj star cj, which is just mod cj all squared, and so we have this simple expression. But that's exactly the result we would have expected based on our previous approach to evaluating the expectation value of a Hamiltonian. So it looks like this works. Our postulated form using the wavefunction operator to rewrite the Hamiltonian has led to us getting the right result for the energy expectation value.